class virtual machines, don't worry, you've got a bit of time. And I'm kind of pitching this at a kind of intermediate level, assuming you're familiar with the basics of Yocto project, how shared state cache can be shared, and how download directories work, things like that. And we've got a little bit of a sysadmin focus to this as we're looking at build automation. So yeah, this talk is going to be in a few parts. We've got the introduction, which is this part. We're going to talk about how to automate Yocto project builds effectively. Then we're going to discuss how you would scale up and scale out that automation. And we're going to look at a low-cost example setup that I've been using for a while now, which also includes public state cache and download mirror, which is accessible for end users. And we're going to conclude with a summary and future work. So, little quick introduction about me. Been involved in Yocto project since 2013. Work across the whole of the embedded software stack, so kernel, U-boot, Yocto project. I'm currently principal engineer at Consulco Group, and there's some contact details there. Consulco Group is embedded Linux and open source consultancy. We're distributed all around the globe with people in several different countries, and we contribute to many of these projects. And just to say quickly, the opinions are mine. They're not that of my employer. I'm pretty heavily involved with the Yocto project, but these opinions aren't canonically opinions of the project. And don't just take what I say. If you're going to spend lots of money on hardware or services, gather performance data and test thoroughly first. So let's start off with automating Yocto project builds. Okay, so simple setup here. What you want is a dedicated build environment for continuous integration or build automation. This should be separate from some sort of developer's machine so that you've not got conflicts happening. You'll need some sort of build script. Now this needs to go and fetch whatever layers you're using, update the repositories, kick off a bit-baked build, and then when that's finished, copy any artifacts that you cared about to some sort of shared storage location where you can access them. You also need some form of trigger to call this script, potentially when new commits push to layers, or potentially on a schedule, so that you can do nightly builds or similar. Other requirements that we've got, well, you want to capture the log output from the build so that you can actually see what's failed and investigate if there's a problem. The other thing you're going to need is a manual command to be able to throw away the working directory used by this build script, and possibly to also throw away shared state cache. That is sometimes needed when debugging issues on some build automation systems. You might need a fresh start to get rid of any work in progress that's been messed up. So there are lots of solutions that can implement this build automation for you. One of the ones that's provided by the Yocto project is the Auto Builder. And this is well tested, well maintained by the project itself. It's based around BuildBot. It is a highly customizable and extensible system though. Other options, you could build your own system around BuildBot, or you could use something like GitLab's continuous integration system, Jenkins, Travis. There's lots and lots of systems that will handle this process of running a build script, which updates some repositories and runs a build, captures the logs and publishes them, and lets you schedule builds to happen on, say, a Git commit or on a nightly schedule. So when we talk about the configuration that you want to put into these systems, my advice is always that the CI configuration should be as simple as possible. Ideally, it would just run one command, and this command would be a build script that you can also run locally in your development environment. Sometimes that's not possible. Sometimes you do need a few more steps in the CI system that you can't just put into a shell script. But the idea here is it allows you to continue working if there is a problem with the CI system. Personally, I like being able to do builds and releases manually if there is a problem with the CI system that we're using, if it breaks or some service that we're relying on goes down. I like to have a script I can just run locally to achieve the same things so that we don't get completely stuck. So the first thing that we want to do as part of this, as I say, is update to the latest version of the layers that we're using. That might be your own BSP layer or distribution layer or some other software layer. But typically you will also have other components that you're pulling in. So that might be Open Embedded Core and Bitbake. It might be the Pocky repository. It may be some other layers that you are dependent on. And there's many possibilities for pulling these in. You can use Git submodules. You can use the repo tool that Google developed as part of the Android project. There's an early layer setup script that TI developed as part of the Arago distribution. And there's CAS, which is a tool that's come out of Siemens, which I'll be exploring slightly later on in this presentation. But at the minute, there is no established standard for this. Depends on your preference, depends on your team and their experience, depends on the workflow that you're trying to achieve. So that's a kind of whistle-stop tour of how we automate a Yocto project build. I've run through it fairly quickly so that we can get into the meat of the presentation, which is, once we've got a single build machine that can run a build on a schedule, how do we then scale this up, scale this out to be able to handle larger teams, more frequent changes, and other things that could be happening within your project. So the first thing we need to do is start breaking down this setup into different components. Rather than just saying, oh, we've got a build script that runs the same as on a developer's workflow, we need to look at these components separately. So we're going to say we've got a build environment, and that's essentially the working directory. It may be includes the dependencies that you need to run your Yocto project build. I think of it as the machine that's running the build as well as the working directory. We've got a state cache that can be stored. We've also got a download cache that can be stored as well. So these typically live in the build directory, but we can redirect these to other locations. We can provide mirrors for these, and we can share them between builds. So the build environment can only be used by one build at a time, but the state cache, download cache can be shared between multiple builds. We also need some artifact storage. So when the build's finished, we likely have some artifacts in the temporary directory, so temp/deploy, that we care about, the reason we've done the build in the first place. We're going to want to store those somewhere a little more permanent. We also want to store the logs that come out of the build so that we can investigate if anything's gone wrong. And we also have what I'm calling the management interface. So this may be a web interface provided by the CI system. So how do we scale this up? Well, the simplest scale up answer would be just replace whatever your machine you're building on with a bigger build machine, just throw more money at the problem. But that's not necessarily the most efficient way of doing things. You want to make sure you're using the right technologies, the right services in order to get the most performant system out of your money. And this may be different from trying to spec out you talk to a server vendor, they'll be used to speccing out web servers. What we're needing is slightly different. But there's some rules of thumb we can use. The first one, in recent years, solid state hard drives have got much better and much larger. You're going to build much faster on an SSD, and you're going to build much faster if that SSD is connected via NVMe. If you're running lots of builds on this, do check the write endurance on SSDs. Typically, they're rated for less than 1 full drive write per day. So if you're writing 100 gigabytes of temporary data every day onto a 100 gigabyte SSD, it may not last very long. You can get SSDs with higher write endurance, but you will pay more for them. The other thing is proper server or workstation hardware is going to perform better than desktop hardware, is going to perform better than laptop hardware. I have seen people sadly putting the CI system on an old laptop in the corner of the office and then wondering why builds are so slow. Please don't do this. Get some proper hardware for the job. If we look at the CPU and RAM requirements, as I say, don't just blindly assume that the more expensive component you can buy is going to be the better component. Look at your build, profile it. Look at the RAM that's being used. Look at the CPU usage over time. Look at whether all that usage is concentrated on one core or spread across the cores. You may have bottlenecks during your build, something like compiling the C library where everything else is waiting for that build to finish. So you want to look at these things and make a judgment as to, in the builds that you typically do in your environment, where do you see CPU usage? If you're seeing single-threaded bottlenecks dominating your build time, you want to look for processors that have the highest clock frequency. If you're not seeing this, you want to look for higher core count. You're going to get more performance out of that. I would also say make sure you use the fastest supported RAM. I've not given a number as to how much RAM you should have. As I say, definitely profile how much RAM is actually being used during your builds. Other factors to consider, a dedicated bare metal build machine is going to perform better than a virtual machine due to the lower I/O overhead. Containers are okay. There's not very much I/O overhead introduced by containers. But if you're using something like Docker, look closely at the documentation. Building inside the overlay FS system used by Docker can be quite slow. You need to set up a proper volume to build in. The other thing you can do is separate the management interface. So if your system has a CI controller and a CI worker or build agent, separate those onto separate machines so that they're not competing for resources. So if you're running something like, say, a GitLab instance and using GitLab CI, don't run your builds on the same host that is serving GitLab. So that's kind of my advice on scaling up the system. The next thing I want to look at is how would we start to scale out. So scaling out is where rather than just having one build machine and making it larger, we start thinking about having multiple build machines. And this requires us to centralize our storage solution. So we'll have multiple agents running builds, and we want a centralized place to store shared state, centralized place to store the downloads that are pulled during a build, and a centralized place to store the artifacts that come out at the end of the build. This can be a network attached storage system. It can be any other storage system you want, really. And I think I'll cover a little more on what we can do for that later on. So there are other benefits of scaling out beyond just being able to run more than one build at once, because we've got more than one machine. One of the things is if you centralize the shared state cache, make it available over a network, then your developer machines for day-to-day builds can reuse that shared state and result in much faster builds for your developers. So that's highly recommended if you've got a team of people and you're doing so much that you need multiple build agents. Definitely share that shared state cache between everything. And maintaining a download mirror is important anyway. It helps you to achieve license compliance because you will have copies of all the copyleft licensed source code that you're using. It also protects you if upstream sources disappear off the internet. This does happen fairly regularly, sadly. And by having your own download mirror on a centralized storage solution, that does protect you and allow you to continue building those components. It also allows you to reduce the potentially reduce single points of failure within your system. If you've got a distributed storage cluster and a cluster of build machines, then you can survive a failure of a single machine. So there's two ways we can look at the scale out. One is a local scale out, the other is a global scale out. So for a local scale out, we're expecting high-speed networking. We could possibly use sort of 10 gigabit or greater networking locally. We're expecting very reliable networking between things. We can use NFS to serve the download mirror and the shared state cache. But if you're looking at a sort of a global scale out, if you've got a distributed business or you've got people in different offices, then you may not be just having one rack with all the equipment in, things may be spread around. So in this case, your network speeds may be more limited. You may see errors accessing shared state cache because of packet drops and transfer errors. And for this, the best technology for serving the download mirror state cache is probably HTTP, and you can update caches over SSH or over some sort of API. Now, if you're doing this, a globally distributed solution, then you're going to need some sort of distributed storage for cache and download mirror and for the build artifacts. And there are many ways of doing this. You can build your own storage cluster to meet your requirements. There are many distributed file systems that are appropriate for this. You could use a cloud service. So Amazon S3 is fairly typical. Other cloud providers have very similar solutions. There are lower cost options like Backblaze. But what I will say is avoid the sort of consumer cloud directory services like Dropbox, OneDrive, Google Drive, all these things. They're good services, but they're really not designed for this use case, and they will have problems. So this sort of scale out really comes down to, you can build this as cheaply or as expensively as you want to. You can do all of this in Amazon AWS with EC2 instances running the builds, using S3 for storage. That will work very well. It will be quite expensive. What I want to explore to finish off my presentation is a low-cost system that can be used for community projects and in cases where budget is a little more limited. And the components of this can be swapped out for bigger and better components as needed. So I always say start with a low-cost solution and then replace things as and when you need to. So the use case for this is our build automation for the SandCloud BeagleBone Enhanced hardware. So this is a piece of open source hardware based around the BeagleBone design with a few modifications. And we support multiple distributions for this hardware. We test Pocky, we test the Arago distribution from TI, and we test automotive grade Linux. So we've got several different configurations to test, and some of those are quite large. So the high-level design that I've used here to implement our build automation for testing builds for the BBE. We use the CAS tool from Siemens to set up the layers, set up the build configuration, which I will discuss in a little more detail in a minute. We use GitLab's continuous integration system to trigger the builds, collect the logs from the builds, and present everything, integrate it with our Git repositories neatly. We have dedicated build servers running the GitLab runner rather than using the free runners that GitLab provides. This allows us to have more RAM and more CPU resources available to build. We use Backblaze as a low-cost storage solution for cache, for mirrors and artifacts. And we use Cloudflare to eliminate the bandwidth costs for Backblaze. So I'm going to run through this fairly quickly. CAS records the build configuration in a YAML file. So it can store the source repositories that you need, and for every repository you have a ref spec that says what branch or what commit of that repository you need. You can store the local patches to apply to these layers. You can set the machine, set the distro, set which bitbake targets you want to build, and set the content of local.conf. The usage for CAS is fairly simple. There's a build command that will build the configuration stored in the YAML file. There's also a shell command that will give you a shell ready to run bitbake. So GitLab CI is then used to integrate everything together and trigger the builds. Again, this uses a YAML file for configuration, and this is stored in the Git repository itself and picked up from the main branch by GitLab. We can store variables and secret values such as API keys in the web interface so that they don't live in the Git repository. And through this, we trigger builds automatically when new commits are pushed and on a schedule so that we can run nightly builds. Build agent, we rent machines from Hetzner in Germany. This is an 8-core, 16-thread machine, Ryzen 7 CPU, 64 gig of RAM, terabyte of NVMe storage, and a gigabit symmetric internet connection. So this is a rack mount system in a data center somewhere that we never have to put our hands on ourselves. We just pay a monthly fee for it and set up the software on it. We install GitLab Runner on this build agent, which has a very minimal configuration. We just need to limit the number of concurrent jobs. The default's unlimited, but you do not want to set off an unlimited number of separate bitbake jobs on one server. That will cause problems. We use the Docker job executor, and then we register this with GitLab. We use the crops container images to actually run the builds in. So when a build is triggered by GitLab, it opens a new container and runs a build in a clean environment. We also use custom images with additional tools for some of our use cases. For storage, we use Backblaze B2. This is a cloud storage solution from Backblaze. They usually provide cloud backup, but B2 is their storage solution. It's pretty cheap. You pay for what you use. You can set cost caps, and they charge very little per gigabyte per month. There's no upload cost. There is a download cost, but we can avoid that by taking advantage of the bandwidth allowance between Cloudflare and Backblaze. So we registered for a free Cloudflare account. We don't have to pay for the Cloudflare account. We're on their free tier. This allows us free downloads from Backblaze B2 via the Cloudflare services. It does require a dedicated domain name, and you do need to, when you set up Cloudflare, make sure you disable the browser integrity check service, since this server will be accessed via the API rather than via someone going to the location in a browser. We use rclone. This is like rsync, but for cloud storage. This lets us copy files up to Backblaze B2 once the build's finished. We store the API key for this in a GitLab CI variable rather than in the Git repository, because we don't want everybody to have the API key used to write to the repository. Monthly costs. We're looking at about €60 per month per server for the build agents we're using. Our storage costs come to $2 per month on Backblaze. There's no long-term commitments on either of these services. We can scale up, scale down as required. So this is a brilliant place to start. Putting these components together gives you a working, scalable system without spending tons of money up front. I did want to have a look through some of the examples of this, but I think I'm running out of time here. So I highly recommend you click through these links. These have got the configuration files, and feel free to ask me questions on Slack or IRC about those. I'm happy to answer for the rest of the day. And I'm going to really quickly wrap up so that we can move on to the next talk. So yeah, this scalable automated system can be deployed pretty cheaply. It does require some system administration work to set up and maintain these systems, and there are many choices available. You can start with the low-cost, simple solutions and replace parts where you see performance limitations happening. And I'm going to finish up there. Thank you very much for your time. I don't think we've got time for questions right now, but as I say, feel free to ask questions on Slack and I will answer them. Thank you very much.